This is Geometry Unit 8. This is day 12. We're working on the circumference and arc length. What's the relationship between a central angle and the measure, that's the key term, measure of an intercepted arc? Remember, a central angle is one with a vertex at the center. The intercepted arc is the arc that's formed by that angle. So the central angle is equal to the intercepted arc. Now when we look at these, what we're going to talk about today is arc length. When we're talking about the measure of an arc, it's the degree value that could be associated with the arc. If your central angle is a certain degree value, say 100, then the arc measure is also going to be 100. If we're looking for an arc length, if you have 100 but 3 different radiuses, the arc length is going to be different each time. So it matters what size of the circle you have. Arc length is the distance, the actual units in terms of centimeters or inches or feet. So the first thing we're going to do for this is look at the measure of each of our central angles. If we take 360, because that's the distance around an entire circle, and divide that into 4 equal measurements, then this central angle is 90 degrees. Take this 360 and divide it into 3 equal pieces, and each of those would have to be 120 degrees. Take 360, divide that into 8 equal pieces, and each of those would be 45 degrees. So that's each of our central angles. We're going to take that central angle and those circles, and we're going to work on filling out our chart down here. So our central angles, we'll put in 90, 120, and 45. So we're going to look at the ratio that's made by the central angle and the total angle around the circle. What is the total angle? What measurement would that be to go around the entire circle in degrees? 360. So if you take 360, that can be reduced down to 1/4, which of course is 0.25. 120 divided by the entire circle can be reduced. If you look at your figure up here, 120 is one of the 3 pieces. So it's 1/3, and that's going to be 0.33, and that repeats. 45 divided into 3, divided by 360. If we look over at our circle with central angles of 45, we see that there would be 8 of those. So that would be 1 of the 8. And that comes out to be 0.125. So that's our ratio for central angle over 360. That by itself doesn't mean anything. We're now going to compare it to what the arc length is over the circumference. We're going to compare those 2 ratios, see if there's any correlation between the 2. So we're going to figure out the circumference. We know to calculate circumference, we're going to look at pi times d. You could even say d pi. So circumference equals diameter times pi. So if our diameter was 4, our circumference is going to be 4 pi. And that comes out to be approximately 12.57. if the diameter is 5, we get 5 pi, which is approximately 15.71. And then if our last diameter for the biggest circle is 6, we'll get 6 pi. That comes out to 1885. Those are the measurements for each of the circumferences of our circles. So up in our chart, we'll say that the 90-degree angle, which has a diameter of 4, is going to be 12.57. 120 has a diameter of 5, 1571. And that largest circle, the diameter of 6, when we calculate that to 3.14, we come up with 18.85. So that's what each circumference is. Now we're going to look at arc length. Well, that's really what this whole lesson's about. It's about how can you calculate arc length. Right now we don't have a way. We're trying to figure out how can we actually calculate it. So we're going to go to the basic old way, where we're going to measure what that value is. So one way we can do it, it's not always very accurate, but we'll take our ruler. We're going to take a measuring, and we're going to go from one part of the arc up to the other end of the arc. Put it on a ruler, and if you're as careful as possible, you'll come up with 3.2. To the larger, we'll go from one arc to the end point of that same arc, which is about right there. Take our ruler, do our measurements, and we'll come up with about 5.2. And then over here to our last one, from one end point of our arc, all these arcs should be the same, to the other end point, the measurement is approximately 2.4. So if that is each arc length, now we're going to take the arc length, which we had to do measuring, which is not very accurate. That's why we're only doing it to the nearest tenth. But still, not super accurate. Let's see how it comes out when we do our comparisons. We're going to take the 3.2, the arc length, and divide that by the circumference, which was 1257. And we'll come up with 0.25. So when we compare those numbers, you see that we get the exact same thing as we did with the angles. You get exactly 0.25. This one's not exact, but the first two numbers are that. We have 3.2 divided by 12.57, and we get 0.25. So it's not exact, because that's it's just the error in doing that perfect measurement for the arc, but it's getting the point shown. So next we're going to take the arc length, which is 5.2, and divide that by 15.71. .2, 1571, and we see that that's 0.33. Again, that's exactly the same value. This one isn't a repeating decimal that goes on forever, like 1/3 would be. This 1/3 would be 0.33333. We actually got 0.3309. It's not exact, but it is extremely close. The best we can do is just trying to measure. 2.4 divided by 18.85. We're going to get 0.127. Not quite exactly it, but again, pretty close. What we're trying to point out is that the ratio of the central angle all the way around the circle and the arc length to all the way around the circle is going to give you the same reduced either fraction, or the decimal is an easy way to read a fraction, so it's very close in terms of the decimal. So we're going to say that the central angle over 360 equals the arc length over the circumference. On the other side, how do the columns in column 2 and column 5 compare to each other? They are about the same. The decimal values were about the same. So that's going to give us a proportion that says arc length, and we'll just pick AB for an example because several of these will have AB as the letters. So arc length over the circumference, and 2 pi r is a typical formula for calculating the circumference, is going to equal your central angle over 360. So that's a good formula to use. Here are some other ways to phrase it. You could do arc length over circumference. There's different ways to say circumference. You could use c. You could use diameter times pi. You could use 2 pi r. Arc length, or I'm sorry, this is arc measure. Arc measure, and remember the central angle are the same measurement. They're equal to each other. So essentially I used central angle. That's a value that they typically give you. But also the arc measure is the degree value that's represented by that amount of the arc over 360. Then you have another version here, all in words. So we're going to try to calculate the arc length of AB. So we have AB over 2 pi r, and that is supposed to equal the angle over 360. So we don't know. That's what we're looking for. The arc length of AB over 2 pi r. 2 pi times 2. The angle is 88, the central angle, as always over 360. So now to solve this, we're going to cross multiply to get 4 pi times 88 over 360, because 2 times 2 times pi is 4 pi. So using our calculator, we'll come up with 3.07 meters. So what that's telling us is our arc length, the distance along the circumference of the circle from A to B, if the diameter or actually here, the radius is 2, then the arc length would be 3.07. Notice that the radius, if we laid the radius out here, it looks a little bit shorter than the orange. Orange looks longer. So 2 meters essentially might come to about here. So then there's a little bit left over, and that's the difference between 2 and 3.07. But you need to use the formula to really be accurate with your numbers. On this one, notice they're asking for the measurement of arc RS. So they're looking for the degree value. And we know that the degree value of the intercepted arc has to be the same as the central angle. So we're going to calculate the value for the central angle. So RS over our circumference, which is 2 pi r, equals the angle, which we don't know, over 360. Well, our measurement we're actually at length. We're looking for the length. The length of RS is 38. The circumference is 2 pi times 12.3. The angle, now there's different ways that we could name this angle. We could name this angle the measurement of angle SQR. You could use measure of angle RQS. You could also name it the measure of angle Q, because there's only one angle that sits in here at point Q. That's at least less than 180 degrees. So we could use one letter for that. So the measurement of angle Q over 360. And if we're solving for that measurement of Q, which remember that central angle is the same as the arc, so that's why we can represent those as being the same. We're going to multiply by 360 to the other side. Now, when you're dividing by these parts that are all multiplied together, some calculators require you to put parentheses around the entire denominator. The graphing calculators for sure would require that. And that's going to come out to be the measurement of angle Q, and you'll find out that that's 177.01 degrees is the measurement of angle Q. Try to be sure that you can use your calculator to represent that answer. For question C, we're asking for the arc length of AB. That measurement, again, very much like letter A, is our arc measure. In this case, this has a central angle of 97. We're looking for the arc length. How far is that if the radius is 4? Arc length over 2 pi r equals the central angle over 360. Notice that each one of these, we're setting it up the same way. So what values go where in our proportion? The arc length is what we don't know. The radius is 4, so we get 2 pi times 4. Central angle's 97. So that could very easily be plugged in. We would cross multiply, and now I'm only cross multiplying one direction because the AB is already by itself. If I was to cross multiply the other direction, the 360 would come up with it. We want the 360 away from it. So we want it divided down at the bottom. Two times 4 is 8, so this is 8 pi. Now that's an exact answer rather than a rounded answer, but that's why we like to use 8 pi rather than trying to figure out what decimal version that represents. 97 times the 8 pi and we'll divide that by our denominator of 360. We get 6.77. And our units are feet. Here we have the circumference of circle Z. Well, this time we're looking for circumference, a little bit different than what we've been looking for before. But remember what your formula is. Circumference is one of the parts. So we're working with x, y, that's your arc measure, over your circumference. And I'm just going to use a c this time rather than 2 pi r or diameter times pi. The central angle over 360. Well, we have 3.44 over c. We don't know what the circumference is yet. We don't know what the radius is either, because if we knew that, we could just use the circumference formula to calculate it. We wouldn't need the central angle or the arc. For the central angle, we see that it's 60, and the denominator is 360. To solve, notice how the c is on the bottom. So I'm going to cross multiply. Then I have to get the c by itself, so now I have to divide by the 60. So we're going to take the 3.44 times that by 360 and then divide that by 60. We get 20.64. And those units are centimeters. That is the circumference all the way around the circle. So if we know what the central angle is and what part of the arc it is, so if you have a slice of pizza that has an angle of 60 and you measure the crust to come out to be 3.44, then you know that all the way around the circle would come out to be 20.64. And you can measure your own by knowing the angle and the length of the arc. You could figure out what the whole circumference would be, or any of the missing parts. On the last page, we'll be using circle D, so that's the center with D. That tells us that that's circle D. We also know that angle ADC is supposed to be congruent to angle BDC. Well, we know the distance around the entire circle is 360. to calculate the measure of the arc ACB, that is everything but the 101. So that's 259. Now if you wanted to know just one of those arcs, remember it's the same as the central angle, then you're going to take the 259 and divide that by 2. So that's 129.5 degrees. Now let's come in and calculate what is the length of arc ACB. How far is that arc all the way through here? Well, we can take the arc ABC and divide that by our circumference, which is 2 pi r. R is 24.9. Central angle of that whole arc is going to be something even bigger than 180. It's the 259 over 360. So when we cross multiply, notice I'm only crossing one way because I have my measure of arc ACB by itself already. Not the measure, but the length of arc ACB. So we're going to get 49.8. That's 2 times 24.9. Pi times the 259. And that'll come out to be 112.56. So looking at our circle, the distance, if the radius is 24.9, the distance from A through C all the way to B, that distance would be 112.59. So if you look at the radius, which is almost 25, you'd have one radius, another radius, a third radius, a fourth radius. So you have 4 different radius, which is 100, plus the leftover, which might be the 12.56. So you can see if it's reasonable for the values. Now we're going to find the length of arc CB. Well, there's 2 different ways we could do that. We could start from scratch and do arc CB over 2 pi r, which equals our central angle, over 360. Our central angle would be 129.5. We could do that. Cross, multiply, and solve. But if we're looking for arc CB, we already know ACB. We know that the 2 central angles are the same, so the 2 arcs have to be the same. So I'm just going to take the 112.56 and divide this by 2. So that comes out to be 56.28. And so I took the full length of the big arc and I divided it by 2 because I knew the central angles were both the same by the given information. That makes both arcs the same. Now we're looking for the measurement of arc ABC. A to B to C. Well, that full arc is 101 plus the 129.5. That's going to give me 230.5 degrees. So let's look for the arc length of BAC. That's also 101 plus 129.5. There's two ways we could do this. We could say the arc length over 2 pi 24.9 equals the angle, which is 230.5 over 360. We could take that and cross multiply and solve. Totally would work. But wouldn't, from BAC, wouldn't the whole thing there be just like the full circumference minus the small arc? And the small arc is 56.28. We already figured the small arc out. So we need this small arc, which is 56.28, and we need this missing arc, which we haven't found yet. So different ways we could think about it. I'm going to take the full circumference we can take the circumference minus the arc CB to get us the measurement of BAC. It's another way we could do it. So we have 2 pi times 24.9 minus 56.28. So this comes out to be 49.8 pi minus 56.28. And using our calculator, we can see that 49.8 times pi minus 56.28 comes out to be 100.17, and those would be meters. So different ways. You have to look at the picture, you have to do some problem solving and decide what method would you use. You could use the method from our notes, which we're going to use proportions, but also know once you start to find some of those numbers, there are sometimes other ways you can calculate it. So we took the whole thing minus the portion we had already found, 56.28. Subtracted that from the circumference. Here's one of my favorite comic strips. It's about Calvin and Hobbes. When Dad comes in and says, "Playing a record? I'll show you something interesting. Compare a point on the label with a point on the record's outer edge." So we have a point on the outer edge, that'll be light, and we have a point closer in. You could even count it this one here. So a point that's not as far out as the other. They both make a complete circle in the same amount of time. So when the circle goes around, this guy starts and goes 360 degrees. This guy starts and goes 360 degrees. So Calvin's like, yeah, I get it. It goes around. But the point on the record's edge has to make a bigger circle in this same time. So this guy's making a big circle. This guy's making a little circle. The two But the point on the record's edge has to make a bigger circle in the same amount of time. So it goes faster. See, 2 points on the disc move at 2 speeds. They're moving at different speeds, even though they both make the same revolutions in every minute. Pretty crazy idea. In one revolution, how much further does a point that is 10 centimeters from the center travel compared to 3? So if it's 3 from here, what is its total distance? If it's 10 out to the edge, what is its total distance? So we're going to take that's a radius. So we have a radius of 3, and we have a radius of 10. So circumference equals 2 pi r. Circumference equals 2 times 3. So your exact answer is 6 pi. Over here, this dot has to make a full travel in 2 pi times 10. So your exact answer is 20 pi. You can put those in the decimals if you want. Now the question is, how much further does the point that's 10 have to travel? How much farther is 20 pi compared to that? So we'll take 20 pi and subtract 6 pi from it. Yes, you could call that 14 pi. That's the distance. That's the extra distance it travels. So 20 pi minus 6 pi is going to give us 43.98, and these are centimeters. So it's going to travel 43.98 more centimeters than the smaller circle. And it still does it in the same spin of the circle. We have Kendra and her mother plan to ride the carousel. 2 horses on the carousel are side by side. For more exciting ride, should Kendra sit on the inside or the outside? Which part, further from the center or closer to the center, is going to make you go faster? Well, we just talked about here, if you're closer to the center, you have a distance of 6 pi. And if you're farther from the center, you travel a further distance. If you're traveling a further distance in the same amount of time, you're going to go faster. By sitting further from the center, Kendra would be making a larger circle. Both horses are traveling at the same speed, so the outside horse is moving faster. And if moving faster is more exciting to you, that's where you want to be.